So to quickly recap, cutting taxes, both on households and firms, will stimulate spending in the economy, will cause the AD curve to shift rightwards. So this is something the government could do as part of its fiscal policy, cut taxes. What about government spending? What should the government do to its spending in a recession, do you think? Increase it, and what would be the logic of that? Government spending. If government spending were raised, wouldn't that directly cause an increase in aggregate demand? Because government is one of the four shoppers. Is that correct? So if the government increased its shopping, well, that by itself would cause aggregate demand of the economy to increase directly. Correct? However, there is also an indirect effect, and this is how it's going to work. There is an indirect effect, and it works through government spending causing an increase in consumption spending. So there is this big indirect effect as well. So there is a direct effect and an indirect effect that works via consumption spending. And what's the logic of that? Well, during the Great Depression, for instance, as we discussed in class last time, President Roosevelt's public works programs, the construction of highways, dams, etc., what did that do? Well, that directly employed lots of people, gave them paychecks, right? What do those people do with their paychecks? Spent it, right? So what do we have here then? An increase in government spending causes an increase in consumption spending, right? All those workers who get paid by the government, all those construction crews, well, they spend their incomes in their local economies, right? So a construction worker goes and spends his money in a local store. The owner of the store gets that money now, right? That's an increase in the store owner's income, correct? And what does the store owner do with that increase in income? Well, he goes and spends at least part of it on something else from another store, correct? My point is that there is this chain effect, a domino kind of effect through the economy. See? The government starts the ball rolling by embarking on these public works programs, right? That puts money into people employed directly by the government, who then spend this money in their local economies, and that causes the ball to roll further and further down the road, you see? And you have this cascading effect on consumption spending. And this is really the subject matter of chapter 14, the expenditure multiplier. You see, as a result of this logic, an increase in government spending has a multiplied effect on aggregate demand. What does that mean? That means if the increase in government spending is $1, then the effect on AD shall be more than $1. The effect on AD should be more than $1 because, you see, the increase in government spending of $1, well, that by itself causes aggregate demand to go up by $1 because G is part of AD. But then you have the indirect effect, you see. And that causes the final increase in aggregate demand to be much more than that $1 increase in government spending. You have a multiplied effect, right? So let's get into the nitty-gritties of this now to discuss the details of this multiplied effect, the expenditure multiplier. Okay? And we're going to use a little bit of elementary algebra here. I need to define a few things. First, I'm going to talk of something called the consumption function. And this is really a relationship between household consumption spending and household income. So what is C then? C is aggregate consumption spending, meaning this is the consumption spending of all the households in the economy combined. Aggregate consumption spending. And we want to relate that to aggregate household income. Now, what would be a measure of aggregate household income? If we added up all the incomes of all our households, what would we get? Does anyone recall? I'd like you to think of GDP by the income approach. If you add up everyone's incomes, what do you get? Don't you remember the circular flow of income idea? What was the circular flow of income? Households spend money on goods produced by firms. All that money enters the cash registers of businesses, and where does it go from there? Back into the pockets of households, doesn't it? Right? So if you add up the income of all the households, what do you get? You really get GDP, do you not? Right? That is the income approach of calculating GDP. If you add up everyone's income in the economy, you would basically end up with the value of all final goods and services produced. Right? So household income then is real GDP. Why? So we have a relationship between consumption spending and household income. And what kind of relationship would that be? Would that be a positive relationship, you think? Or a negative one? In other words, if I had consumption spending as some sort of function of income, household income, what type of a relationship would this be? Would this be a positive relationship? Meaning, if income goes up, would consumption spending go up? If your income goes up, wouldn't your consumption spending go up? Well, if it's true for you, it's true for all of us combined, isn't it? Right? So this then is a positive relationship. And to make things simple, we are going to make this a linear relationship. This is a simplification. So in other words, we're going to have a straight line relationship. In other words, if I had to plot, if I had to make a graph like this with consumption spending on the vertical axis and household income on the horizontal axis, I'd like a straight line. Right? So what kind of an equation do I need now, this function f of y? What might be a good way to put this? Now, what's the equation for a straight line? The equation for a straight line, you recall, is y is equal to mx plus b, right? So we're going to put things in this form. Now, what is our y? Our y, what are we measuring along the y-axis, the vertical axis? Come on. In our case here, what are we measuring along the y-axis? That's the y-axis, isn't it? And this is the x-axis, correct? So what are we measuring along the y-axis? Consumption spending. What are we measuring along the x-axis? Real GDP. Right? So we're going to write it in this form. C is equal to C sub 0 plus B times Y. So what is the C sub 0? That's like this intercept. This is the y-intercept. What is B? B is the slope. That's like the m in this equation for a straight line. Correct? So in terms of this graph here on the left, what's going to be C sub 0? C sub 0 is this. That's the intercept on the y-axis. And what about lowercase b, the slope? Well, the slope would be this slope. That would be the b. Sort of that angle. Correct? So this is our consumption function. It's a relationship between consumption spending in the economy and household income. Household income, of course, is nothing but GDP. Why? By the income approach. Now let's understand this function. Okay? Firstly, why is C0 a positive number? In other words, why do we have this intercept? What's the meaning of that intercept? How would you interpret the intercept C sub 0? C sub 0, by the way, is called autonomous consumption spending. Autonomous consumption spending. What does the word autonomous mean? Autonomous means independent. So this is the part of consumption spending that is independent of household income. It doesn't depend on household income. Household income could be 0, and yet people would consume so much. Is that correct? In fact, that's what C0 means. If household income was 0, in other words, remember, you have C is equal to C0 plus B times Y. If household income was 0, what would happen? Wouldn't C simply be equal to C0 then? Because B times Y would be 0, Y being 0. Is that right? So what is the meaning of C sub 0? What is the meaning of autonomous consumption spending? So this is C when Y is equal to 0. Now, why do you expect that to be a positive number? When household income is 0, why wouldn't consumption fall to 0? Why does it continue to remain something positive? What's the simple logic for that? Any thoughts? When household income falls to 0, why do people continue to consume? Because they must, you see, to live. If you lost your job today and your income fell to 0, would you simply stop consuming, stop eating? No, right? That's the logic behind this. If income were to fall to 0, you would still have some positive consumption. What would finance that consumption? If you have no income, how would you eat? Now, what's true for you is true for all of us in the aggregate, correct? So if you lost your job and your income fell to 0, how would you finance your consumption? Your essential survival type of consumption. How would you finance that? With credit, or you would use any savings that you possess. Am I correct? So this kind of consumption is financed by what's called dis-saving. And what does dis-saving mean? It's the opposite of saving. Dis-saving can mean either borrowing, or it can mean running down your savings. If you have any savings, you start to use them up. If you have no savings, you would of course have to borrow. So this saving consists of both those things, borrowing as well as running down existing savings. So that is how C0 would be financed. So that we have an understanding of autonomous consumption spending, C sub 0. Now let's talk about the B, the slope. So let us now talk about this. We have dealt with this, correct? So how do we think about that slope? Now, firstly, what is the meaning of that slope? How would you interpret it? Now, wouldn't the meaning of the slope be the standard meaning, which is change in C from a $1 change in Y? Isn't that what slope means? It's a change in the variable you're measuring along the y-axis that results from a 1-unit change of the variable measured along the x-axis. Isn't that right? Correct? So that's the meaning of the slope, the change in consumption spending from a $1 increase in income. Now, let's ask ourselves the following question. If our income, meaning one of you, if your income rose by $1, Okay? So if your income rose by $1, by how much would your consumption spending change, do you think? Now, if you have difficulty visualizing this, think not of a dollar increase, think of $100 increase or $1,000 increase, correct? So if your income went up by $100, your weekly income, let's say, by how much would your consumption spending go up? Do you think it would go up by the entire 100? Would it perversely go up by more than 100, which would be the case when your income goes up but you get deeper into debt? It happens to some people. Where you get a rise, but you increase your spending by more than your rise. Right? But what's typical, do you think? If your income goes up by $100, would your consumption spending go up by exactly that 100? Less than that 100? Or perversely more than that 100? What is your sense of that? How do you think the average American would behave? Any thoughts? Well, the average American would behave, according to economists, in the following way. They would try to save at least a small part of this increase in their income. Do you follow me? So a rise in C by, a rise of income of $1 would cause C to change by less than $1, e.g., 90 cents. Economists believe that most Americans behave that way. If you think of your average Joe, that's how the person would behave. If you gave him an extra $1,000 of income, this person would increase his or her consumption spending by $900, saving $100. If you gave him an extra $1 of income, he would increase his spending by 90 cents. He would save 10 cents. Okay? We have a name for this 0.9. We call this 0.9. We call it the marginal propensity to consume, or the MPC. So what is the MPC then? What does the MPC mean? The MPC is the change in consumption spending from a $1 change in income. Change in consumption spending from a $1 change in income. Now, isn't that nothing but the slope B of the consumption function? Isn't that how you define slope? Go to the previous slide here. What is the slope again? Isn't that the definition of the slope? The change in C from a $1 change in Y? Yes? So we now have a formal name for that. The slope B is nothing but the marginal. It's nothing but the marginal propensity to consume. That's the slope. And many economists believe that in the States that's about 0.9. Now this MPC is going to play an important role in our story, our multiplier story. I'm going to go to a new page. So let's say that FDR, let's go back to the Great Depression, and let's say that FDR increases government spending by $1. He decides to spend an extra $1 on building the Hoover Dam, for instance. Let's analyze the effect of this on aggregate demand in the economy. So let's make a little calculation here. Change in aggregate demand. Well, what do we have here? If government spending is going up by $1, government spending being a part of 80, immediately we have a dollar increase. Is that correct? What is that dollar increase? That, in fact, is nothing but that dollar. Right? Because G is a part of AD. So when G goes up by $1, AD goes up by $1 automatically, directly. That's the direct effect. So this here is the direct effect. But as I've told you, the ball doesn't stop rolling at this point. It carries on. Am I correct? Because this $1 will enter the pockets of the construction crew building the Hoover Dam. Right? Now, what do these workers do with this dollar increase in their income? All of it? What part of it? We've just talked about this. 0.9, am I correct? The MPC, that's the meaning of the MPC, right? The MPC, the marginal propensity to consume, is the increase in consumption spending that results from a dollar increase in income, right? So the construction crew that receives this extra dollar of income will not spend all of it, will spend a part of it. What part of it? The MPC part of it, correct? So you would then have a further increase now of consumption spending of how much? So what is this? This is an indirect effect, which is an increase in consumption spending. So the workers spend 90 cents of that extra dollar of income on, let us say, bread from the baker in the community in which they live. Right? So they spend 90 cents on extra bread from the baker. The baker receives this 90 cents now. And that 90 cents becomes part of the baker's income. What does the baker do with this 90-cent increase in his income? Well, what do people do with increases in their income? They spend what percent of it? What percent of it do they spend on consumption? 90%. Is that correct? Because the MPC is 0.9. So the baker will spend how much of this 90 cents on, let's say, meat from the butcher? How much? 90% of 90 cents. Is that correct? And how much is that? Couldn't you write this as 0.9 squared, which is 0.9 times 0.9, or 81 cents? Do you understand what's going on here? Is that clear to you? So remember that the whole story started with the government, FDR, spending an extra dollar on construction of the Hoover Dam. This dollar went into the pockets of the construction crew. They then spent 90% of it on bread from the baker. Why do they spend 90%? Because the MPC is 0.9. Is that correct? The MPC is 0.9. This is where the 9.9 is coming from. Right? Now the baker gets this extra 90 cents of income. What does he do with it? He in turn spends 90% of that increase in his income on meat from the butcher. So you have a further increase in consumption spending. So this is spending by whom? The baker on what? Meat from the butcher. So you have a further increase in consumption spending. Of course, the ball doesn't stop rolling there because now the butcher gets an extra 81 cents of income. Right? What does the butcher do with this extra 81 cents of income? Well, he in turn spends 90% of it on something else. Let's say vegetables from the produce guy. You see where this is going? So you'd have another number next to this, which would be 90% of 81 cents, and you could write that as 0.9 cubed. Right? Of course, the story doesn't end there either. This just keeps going on and on. You have a sequence here which basically keeps going on and on and on and on. To where? Where does it stop? It doesn't have a stop. It just carries on. You would in the end have 0.9 to the power infinity. Correct? So this would be the change in aggregate demand as a result of FDR increasing government spending by $1. Now the question is, can we add up this sequence of numbers? Can the above sequence of numbers be summed up? Because that is going to give us what we want, which is the total increase in aggregate demand. Is it possible to add up a bunch of numbers that go on forever? Well, typically no, but in this case, yes. I'll tell you why. Because as you get further out in this sequence, the numbers become really small. Now, how am I sure of that? I'm sure of that because you notice already that each number is smaller than the one that comes before it. $1, 90 cents, 81 cents. The next number would be 0.9 cubed, which would be 0.73 approximately. So these numbers are becoming smaller as you go out in the sequence. So as you go out in the sequence, the numbers become so small that in a sense adding them up is not going to change the sum by very much. Right? So this sequence has a name. This is called a converging geometric series to infinity. This is a converging geometric series to infinity. Now, geometric series have something called the factor of the series. Factor of the series. And what's the factor of the series? The factor of the series is the number that you multiply each number by to get the next number. So what would be the factor of this series? The number that you multiply each number in the series by to get the next number of the series. So what's our factor? Come on, I need some action here. I seem to be delivering my lecture to a rather sleepy audience today. What's the factor of this series? Somebody. Come on. Did you not hear what I just said? What's the factor of the series? It's the number that you multiply each number of the series by to get the next number. Come on, tell me. What did I need to multiply 1 by to get the next number? Come on. 0.9, right? And what did I need to multiply this by to get the next number? 0.9, exactly. Now, work up a little, will you? So 0.9 is the factor of the series. Is that correct? So what is the formula for adding up a geometric series to infinity? There is a formula. We can derive it, but I won't. And the formula for adding up this series, to sum up the series, the formula is the following. The formula is the first number of the series divided by 1 minus the factor of the series. This is a formula for adding up a geometric series, a converging geometric series. It's important that the series be converging. What does that mean, converging? That means the numbers are becoming closer and closer to 0. They're converging to 0. Correct? So let's add up this series and using this formula. So what is our change in aggregate demand going to be then by this formula? Come on. I'm going to wait for you to come up with this. First number of the series divided by 1 minus the factor of the series. So what do we have? What's the first number of the series? 1, exactly. 1 divided by 1 minus what? 0.9, exactly. And can somebody tell me what that is? That's 1 divided by 0.1, isn't it? And what's 1 divided by 0.1? The same thing as a 10 divided by 1, isn't it? Right? So the answer is $10. In other words, by FDR increasing government spending by $1, in the end, we end up with an increase in aggregate demand of how much? $10. So the direct effect is how much? Is simply the $1 increase in government spending. The indirect effect is how much? $9 of consumption spent. You see? So there is this huge multiplied effect of an increase in government spending. That's the theory. Is this understood? 1 divided by 1 minus 0.9. So we can now do the following. So we can say that if G rises by $1, aggregate demand shall rise by how much? 1 divided by 1 minus, I'm going to keep it general now, I won't say 0.9, I'll simply go MPC. Yes? Now this thing here, 1 divided by 1 minus the MPC is called the government spending multiplier. It's called the government spending multiplier. And what is the meaning of it? The government spending multiplier, what is it again? It's the rise in AD from a $1 rise in government spend. Now, if I were to give you a little problem, a little math problem, if I said the government raises its spending by $700 million, which was approximately the size of President Obama's, sorry, that was 700 billion, I'm sorry, not million. But let's say the government raises its spending by 700 million. 700 billion was the size of Obama's stimulus package back in 2009 or so, when he was trying to bring the economy out of the Great Recession. Right? So if government raises its spending by 700 million, could you calculate the change in aggregate demand, assuming the MPC is, I'm going to give a number like, say, 0.8. Could you do this problem? Government raises its spending by $700 million. $700 million can, of course, be thought of as 700 million single dollars. Is that right? And each of those dollars will have what kind of an impact on AD? Each of those dollars would increase AD by how much? By so much. Is that correct? That would be the effect on AD of each of those $700 million. So all 700 million together would have what kind of impact on AD? Wouldn't it simply be this times 750? Am I making sense? Because this circle thing here is the effect on AD of a single dollar increase in government spending. But in this case, government spending is going up not by a single dollar, it's going up by 700 million single dollars. So what's the effect of the $700 million increase in government spending? It's going to be 700. Correct that. Yes? So the formula, then we can write this formula as follows. Change in AD is equal to change in government spending times the government spending multiplier, which we know to be 1 divided by 1 minus the MPC. So what would our answer be here? Our answer would be, what's the change in government spending? Plus 700 million. Why do I put the plus? Why do I put the plus there? Because this is a rise in government spending. An increase is a positive change, so I put a plus there. You see, because the government could well have been decreasing its spending, in which case there would be a multiplied decrease in AD. Now we multiply this by 1 divided by 1 minus, what's the MPC in our story? 0.8. So we have plus 700 million times 1 divided by 0.2, which is plus 700 million times 5, which is plus or plus 3.5 billion. Correct? So according to our story here, a $700 million increase in government spending causes a $3.5 billion increase in aggregate demand. Now let's come back to our aggregate demand diagram. Okay? I'm going to quickly here draw an aggregate demand curve. Let's not forget that diagram. Okay? So we have here, this is our aggregate demand curve, correct? Real GDP, price level, this is our AD curve. So what's happening here? If we have this large increase in aggregate demand, how are we going to show that in this diagram? Shift it to the right, correct? So we would shift this curve to the right like this. Now you tell me what this horizontal distance is going to be. This is the increase, is that correct? So what is this horizontal distance? This is the actual change in AD, isn't it? How much is that equal to in this case? $3.5 billion. That's how you show it, you see. You have a $3.5 billion increase in AD, which is then a horizontal shift rightward of the AD curve to the tune of $3.5 billion. So we've dealt with the government spending multiplier. We will stop here today because I don't have enough time to launch into our next multiplier. We'll do this on Friday. Stop here today.